Hello everyone, welcome to another episode of this series, and today we're gonna be doing this question, and this is from the textbook A level, this textbook A and AS level physics, chapter 6 momentum. It is in the end of chapter questions. So yeah, now let's get straight into it, right? So number A, state the principle of conservation of momentum and state the conditions under which it's valid. So the principle of conservation of momentum means that the momentum before the collision or before the event is the same as the momentum after the collision or after the event. That means that the momentum cannot be created out of thin air, momentum cannot be destroyed. It's just like the conservation of energy, but it is momentum, right? And then it is all valid if the system is closed. If the objects are affected by external forces like air resistance or frictions, it won't work, right? It will be like violating the conservation of momentum. It is because there are external forces such as air resistance and friction, right? So yes. Let's go to question number B. An arrow of mass 0.25 kilogram, so 0.25 kilogram, 5 kilogram, is fired horizontally towards an apple of mass 0.1 kilogram, so 0.1 kilogram of mass right here, which is hanging on a string, okay? The horizontal velocity of an arrow as it enters the apple is 30 meters per second. The apple was inertially at rest and the arrow sticks to the apple, okay? And I have to calculate the horizontal velocity of the apple and arrow. So I have to find the horizontal velocity of the apple and the arrow here. So how this is gonna work? You're gonna be using conservation of momentum to use it, right? So let's calculate the momentum of the arrow, or we have to find the momentum of the total momentum before the collision. And since apple is at rest, it doesn't have momentum. Remember, if momentum is mass times velocity. If velocity is 0, then momentum will be 0. So to find the arrow's momentum here. Okay, so find the arrow's momentum. Alright. Momentum mv, mass is 0.25 kilograms, and then velocity is going to be 20 meters per second. And then if we use the calculator to solve this question, it will be about 7.5 kilogram meter per second. So the arrow momentum is going to be 7.5 kilogram meter per second. So according to the conservation of momentum, the total momentum before the collision is the same as the total momentum after the collision. So that means that when the arrows and the apple sticks and then they have a horizontal velocity, that momentum, so that combined momentum after the collision is going to be 7.5 kilogram meter per second. Because of conservation of momentum. I hope you guys get that. So let's say that momentum after the collision. So let's say, I don't know, PV or something, I don't know. The collision is gonna be 7.5 kilogram meter per second because of conservation of momentum, right? So yeah, we just need to calculate the velocity here. So we have the 7.5 and mv. Like we don't know the velocity, but we know the mass. And since the arrow and the apple sticks together, we have to combine their masses. So 0.25 plus 0.1 and v. So whenever we want to find the velocity, we just divide that, and I'll just do that in the calculator here. Calculator is very, very handy tool, dude. Like, I wouldn't survive high school without this, for real. So the final velocity is gonna be 21 0.4 meter per second. So after the collision, the apple and arrow sticks together and they both go at a horizontal velocity of 21.4 meter per second. Alright. So it's only a horizontal because there's a string here, maybe there's a string or something here, right? So maybe there might be some vertical component. I don't know, I'm not sure about that. Yeah. Question number 2. Let's use a different color. Calculate the change in momentum of the arrow during the impact. Alright, so how do we think this is, right? So to calculate the change in momentum, we have to calculate the momentum before the collision, and we calculate the momentum after the collision of the arrow. So we have this. So let's calculate the momentum before the collision, and we already did that. It's 1 kilogram meter per second. So we're going to use this right here, right? So B. Then we're going to use it right here. And then to find the momentum after the collision, right? And then it's only the arrow that we're talking about. It's only the arrow. It's not the apple. It's the arrow. So it's only the arrow. So the mass, we have to only calculate with the mass of the arrow, and we don't need to add in the mass of the apple because they only ask for the arrow. I hope you guys understand that. I mean, I'm doing really bad at explaining right now. I'm sorry. I am really bad at English too. So this is before. This is before the collision. It's gonna be about like 7.5 kilogram meter per second. And then we do calculate the momentum after the collision. So let's find the after the collision, right? So mv, the mass, we only need to use the arrow's mass, and for velocity we have to use this velocity that we just calculated, which is 21.4 meter per second, and we just calculate that, and then that would get us about like 5.35 kilogram meter per second. And as you can see, momentum before the equation and after the equation is the same thing. But won't that break the conservation of momentum? No, because we're not calculating the apple. We are only calculating the arrow's momentum, not the apple's momentum too, right? So that's the key here. So we're going to find the change in momentum. So we're going to do this. It should be the easy part here. 7.5 minus 5.35, and then that would get 2.15 kilogram meter per second. Alright, so let's move on to question number 3. Actually, we are gonna, oh my god. wait. B1. This is B2. It's not. Oh my god. So pardon me, guys. I'm sorry. I don't really pay attention to those details. So then let's go to question number 3. We need to calculate the change in total kinetic energy of the arrow and the apple during the impact. So we have to find the total kinetic energy change of the arrow and the apple. So that means that oh god, sorry. That means we have to calculate the total kinetic energy before the collision, and then we have to find the total kinetic energy after the collision, and then we have to subtract those two values to get the change in kinetic energy. Okay, so the kinetic energy of the apple before the collision is 0 because it's not moving. So we only calculate the arrow's kinetic energy. So yeah, let's do that. Let's write it right here. Okay. So the kinetic energy, I'll just write it. Oh no, never mind. before kinetic energy, right? Then that would be about 1/2 mass. We use the arrow's mass times the velocity, and then that will get 1/2 is 125 30 square. 125 5 joules here, and then we have to calculate the kinetic energy after. So after kinetic energy is gonna be 1/2 mass is gonna be like, look here, total kinetic exchange of the arrow and the apple. So we have to use the combined mass between those two. So we 0.25 plus 0.1, and then the velocity square. So total velocity, we'll use this again, 31.4 square. So if we calculate it, and also in the calculator, we will get about, wait guys, 0.1, about 80.143 joules. Okay, so now to find the total kinetic energy or change in kinetic energy, change in K or K, well, what am I writing? KE, that is gonna be 112.5 minus 81.124, 143, bro. So that would get 1, 2, 5, 4, 3, about like 32.3 or 4 joules of energy. So then that'll be the change in kinetic energy. So you can say this, you can add the minus sign here because kinetic energy is reduced or lowered. So that's gonna be, yeah. Okay, so last question, an identical arrow is fired at the center of a stationary ball of mass 0.25 kilogram. Okay, so same mass. Same mass. Alright, yellow is in a good color. So same mass, the identical arrow, stationary ball. So okay, the collision is perfectly elastic. So that means that, so when the arrow, let me draw a beautiful arrow here. That's not beautiful. And then there's a stationary ball here, gonna be at the middle. Imagine it's gonna be at the middle, and they both have the same mass. And yeah, they have the same mass. There's no spin. There's not gonna be spin effect because it is at the center, right? Fire at the center. Describe what happens and state the relative speed of separation of the ball. So you can think of this like a billiard ball or something. I don't know how you say that in English, but billiard ball or something. You know those like eight balls or something like that, you know? So when one ball hits the other, like with no spin, what happens is gonna be like, imagine here, ball 1 and 2. It hits, and then what's happening is ball 1 is gonna be stationary and ball 2 is gonna go at the same speed. Right, basically because they have the same mass, no spin, and perfectly elastic, so no reduction of kinetic energy, and no bouncing back. And ball 1 is gonna stop, and ball 2 is gonna move. Basically, like ball 2 borrowed the kinetic energy from ball 1. Yeah, it will be the same case for the arrow and the ball. Right. So arrow will stop moving. So it has the velocity here, but arrow will stop moving, and then the ball will pick up and go to the same direction as the arrow with the same velocity. Right. of the two objects are the same. So that's why it works, and it's perfectly elastic. So you just need to describe that, and the relative speed of the separation is going to be 30 meters per second. Because of this, the relative speed, so it's 30 meters per second for both the arrow and the ball. And yeah, that's it. So guys, yeah, I hope you enjoyed the video. And yeah, I'll see you guys tomorrow, guys. Have a great day. Goodbye.